Hello, I'm Patrick Hammer, and today I will present to you the demonstrator project Scavenger, real-time logic-based control for an autonomous scavenger robot. This project has the principal investigators Jano Domova from RPL and Lei Feng from the mechatronics department. Patrick Hammer, Robert Johansson, and Peter Isaev are collaborators, as also shown in the pictures here. The core of this project is motivated highly by, as Stephen Walker puts it, today's machines lack contextual reasoning capabilities, and that training must cover every eventuality, which is not only costly but ultimately impossible, which is stated in the AI Next campaign of DABA. And so the question is, how can we improve on this? And several research challenges arise from this. Our approach is to integrate logic-based planning and real-time reasoning into the picture together with advanced control algorithms. So we hope that this improves the autonomy so that the robot can perform tasks autonomously in real time in an adaptive, data-efficient, and energy-efficient way. And for this, we provide an open source package which everyone can download using a robot operating system. So it's easy to integrate also in other hardware. And what we also show in this project is autonomous waste collection in the Aarhus, in the city of Aarhus, which was supported by Aarhus City Lab, and the test bed they provided to us. The architecture looks like that. We have LTL, linear temporal logic planning on the top, which has a mission specification, and NAS receives this. NAS is a non-axiomatic reasoning system, which essentially operates on the robot and tries to get the mission accomplished using various real-time control approaches, like for actuator control and various sensor fusion abilities, as we will see. Overall, we really try to have three different components here, which is this long-term planning with linear temporal logic, then this on-board reasoning with NAS, here the system especially provides real-time learning and reasoning and decision-making on the robot and can achieve mission goals. And also, it's important to point out that also sophisticated control algorithms are necessary for actuator control and so on. So all of the project members are well represented here. And we show the effectiveness of our solution in a waste collection task in Aarhus, where the robot essentially is employed to collect waste objects like bottles and cans and cups autonomously. So from reasoning perspective side, there's the non-axiomatic reasoning system is quite special, since it's a reasoning system which is designed to operate in real time under finite processing demands. So the system can continue to receive information, will not get slower or not get stuck into planning loops. It's really meant to operate the hardware in real time, so that it can also react to current events. And GEOS is also a special logic, namely non-axiomatic logic, which allows the system to deal with uncertainty. So it's can actually also deal with cases where the environment might not always be as predictable as wanted, or where uncertainties arise on sensory side and so on. This can all be captured. And in this project, we integrated this reasoning system into the robot, supporting various sensory fusion. We have like a object detection model, YOLO version 4 there, running on the robot graphics card. We have simultaneous localization and mapping with 2D LiDAR sensor. And we also have a manipulator arm, as you can see here on the left, which supports the picking of the objects. Also, there's this information from this different sensors goes into the NAS reasoner as events, which the reasoning system can incorporate in its decision making, where the decision making has a relatively simple motor interface that allows the robot to turn to the left, to the right, to move forward, to go to certain places using the ROS navigation stack, and to pick and drop objects using its manipulator arm using control procedures. The testing in RHOS, we already carried out the first testing phase. The testbed, which was provided by RHOS City Lab, is particularly one of the largest robot testbeds of that kind in Europe. And it contains a recreational area, parking area, and football field. And for the reproducibility of the tests, we have particularly focused on the test bed in the middle, football field, where we placed objects like cups and bottles and of different materials, glass, plastic, and paper, and the object depths mentioned before, and the scene looks like here. You can see here. And overall, the mission is like that. You essentially want the robot to move around in the environment and to be able to find objects. For this, it needs to be able to navigate the environment. It needs to be able to build a map of the environment, remember locations of which it has to traverse, and in that, it has to be able to detect the trash objects of relevance, and then to pick them up and to put them into the trailer, essentially. And the real-time reasoning system has to control this process, has to make the decision-making, and invoke the control procedures. So we run this on the test bed. Here on the right, you see like the output from the object detection. Also on the right, navigation and mapping using G-mapping algorithm. And this looks like that if we run it. So the robot is driving around. It has detected now some trash object, which it now tries to pick up. So it's now trying to focus using the control procedure, getting the object into the middle of the gripper so that it can be picked up. Also making the distance smaller by moving closer to it, and then trying to grab it. There's also feedback control involved, where it tries to get from the sensor reading if it actually has an object in the grabber, and when it has confirmed that, it begins to rotate around to put the object into the trailer, and that's essentially what it has to do. And it has to, in addition, it has to traverse through certain test beds and through certain checkpoints in the environment, so that it can pick up trash at the various places in the test bed, essentially. So that's about that. So here now it moves to the next checkpoint. Overall, the test procedure was set up in a repeatable way. So we always placed it at the same starting point. We placed the same object at the different checkpoints within the scene. And we established a circle. We set up the checkpoints in a circular route through the test bed. And we also provided the reasoning system some background knowledge, like how to move to the next checkpoint, to pick up trash when it identifies it, also giving it categorical information about which detected object categories can be seen as trash, should be seen as trash, and also to drop the objects into the container once they have been picked up. The test results seemed very promising. It's not perfect, but at least we get a 68% task performance result here, which is really indicating that about slightly more than 2/3 of the objects, trash objects in the test bed, it was able to pick up. And we also compared with a belief desire intention model with planning approach in comparison. And what we can show is that because of the evidence updating of this reasoning system, since it handles uncertainty, it's really able to learn, okay, if a specific object has been tipped over or cannot be reached anymore, it will update the evidence and realize, okay, it's time to move on to another object because this doesn't work. Well, traditional planner, if the plan precondition is still met, it will repeatedly try the same operation unless it's explicitly programmed to handle this case. But one of the nice features with this reasoning system is that it can deal with unexpected situations, like here, where it really has to update the evidence of the even the knowledge we give it. Here, it learns both the objects and which ones can be picked and or not be picked. And it also learns additional information, like where in the testbed trash objects accumulate and where not. So there are some desired capabilities here. Overall, there's a wider story here. On one hand, we provide the open source package for the wider community, robotics community to be utilized. Then we also have a publishing in robotics venues and conferences, the results we have obtained. And we will further approach cities and companies for which this increased autonomy in robots can make a positive impact, which could be useful to them essentially. And here we really have the long-term vision so that we have low-cost, energy-efficient waste collection and infrastructure inspection carried out in an autonomous way with as little human intervention as possible. Thank you very much for listening.